So a warm welcome again to all of you to today's user preparation, EUMETSAT user preparation webinar on EPS-SG multi-viewing, multi-channel, multi-polarization imaging mission 3MI. So this is day 2. So those of you who have been here with us yesterday, I welcome you back, and I hope you know how it works yesterday and how it worked yesterday. It's the same style today. And for those of you joining today, I will give a brief introduction. So these are, I'm Srireka Thoniparambil. I am the User Preparation Manager at EUMETSAT for EPS-SG, our next generation polar satellite program. And I'm organizing this webinar together with Stefan Buczynski. He is our MTG User Preparation Manager. Like EUMETSAT is launching this, MTG is our next generation geostationary satellite program. And both these satellites are equipped, these satellites will be launched in the coming years. You will hear more about them. And both these satellites are equipped with heritage missions as well as new missions. Heritage missions, obviously, with enhanced capabilities. And with these user preparation webinars, this is the fifth one in this series of user preparation webinar series that we have organized. And with these user preparation webinars, we intend to inform our users to give a more in-depth information on all observation missions that are on board these geostationary and polar orbiting satellites. There's some more to come. They will come. We take a break during the summer, and then we'll be back in autumn with the microwaves and the radio occultation instruments. And on day 1, we had Thierry Maba, who was introducing 3MI instrument and how 3MI measures the radiation from Earth in different viewing angles across several spectral channels, and also how it measures the polarized radiation. He also talked about how the level 1 products are generated, calibration, a bit about the dissemination, and also introduced the 3MI test data that the users can play with now before the launch. And today we go a step ahead and we talk about the level 2 products from 3MI, so mainly clouds and aerosol product generation, then how they're generated, and how useful they are. We also talk, like I said yesterday, 3MI is contributing towards climate monitoring to a great deal, the aerosol and cloud observations mainly. And in this regard, we have also a talk looking at the prospects of reprocessing from 3MI. So this is how we have organized today. And with that, I think the experts will talk to you more about this. And before we start with the first talk, which is Bertrand's talk on the level, where he will give an overview of the level 2 products, I just give you a bit more information on how to interact, basically how you can ask questions. So there's a tool called Slido. You can type in your questions there, and you need to put in a code. And if you look at the chat, the chat window has some instructions on how you can do it. It's very simple. Put your questions in there, and they will pop up after the talk. And the Zoom chat, just contact us if you have any issues with connections or any problems with audio, etc. And one more point, we will give out all the presentation slides and the recording together with the Q&A. So some of the questions, like in today's, we have several talks today, so I don't know how many questions, put in your questions, and if you're not able to answer them live today, we will take them offline. We'll give a reply to all your questions. So these questions, together with the recordings and the presentations, will be made available to you some days after the event. We just need some time to process all these. So that's it. And then you will get them. And with that, I hand over to Bertrand. Bertrand, you can show your video and start speaking.
Yes, can you see my screen?
Yes, your screen is in full screen mode and it can be seen.
Okay, good. Thank you. Hello to everyone. I'm very happy to give you this quick introduction of the 3MI level 2 product and the generation. It's on behalf of the team working on cloud and aerosol development in EUMETSAT. Okay. So, three aspects that I will just browse quickly. First, to recall you what is very specific on the 3MI information content. I think it's important to have that in mind. Then after, we will have a look on the level 2 processors as they are implemented today on the ground segment. This is what we call the day 1 product. And this is done for aerosol and cloud aspect. And then after, we will see the more or less the future with the development of the day 2 product, so the next version of the product, and the improvement that we foresee for aerosol and cloud. So first, yesterday you had, for those of you who were there, you had a very good overview, a detailed overview of the 3MI concept, design, and everything. So just in one slide, I remind you what is this concept. It's just a wide field of view optic, allowing a long track to have multiple times the same acquisition of a ground target with different viewing angle. And on top of that, we have, of course, the spectral and the polarized information, but this is the concept of this type of acquisition. And so this is a multi-view, multi-polarized, and multispectral acquisition. So it's a very specific type of acquisition that is not so usual. And as you can see on this animation that I like, you can see on the left a normal, I would say, a standard acquisition of an overpass over Europe. And on the right, you have the same thing, but viewed as a polarization. And you immediately see that it's completely different in terms of information. And this is why, also including the variation with the geometry is completely different. And this is why the combination of the three, spectral, directional, and polarized, is very useful for the retrieval of of the particles that populate the atmosphere. So aerosol and clouds typically. The information content is very large because we have 14 views, 12 bands, and 3 polarizations. So typically 400 different information that we can try to use to feed the retrieval for clouds or aerosol. So this is the same type of information, but shown with simply plots. You see the way the spectral, the directional, and the polarized information or signature is changing a lot sometimes, depending on the population of aerosol you have in that case. But this is exactly the same for cloud. It depends on the microphysics of the particles and the quantity of particles, of course, but also the type of the particles, the phase, the size, the shape, the absorption of the particles. So many parameters that influence the optical properties of the clouds and the aerosol. And this is exactly what we use on the retrieval to retrieve these aerosol and cloud properties. So the general scope for the level 2 processor is we have today under development, under implementation, 2 processors for cloud and aerosol, and they are under implementation on the operational ground segment, the EPS-SG ground segment that is called the Payload Data Acquisition and Processing, PDAP. These products under implementation today are called day 1 product. It means that they will be available at the time of the launch of the satellite, the first generation of product. They are developed as a near real-time product, so it means they will be available typically 1 hour and a half after sensing. And because they are implemented today on the ground segment, they must rely on very mature approaches for this first generation. And this is why we rely on the strong heritage that comes from the polar and partial mission, including the synergy that was done with the A-train sensors, like MODIS, for example. So even if 3MI is completely new in EUMETSAT, the heritage is very strong, and it comes from the scientific community and these predecessor missions. So the aerosol is the core scientific mission for 3MI, but of course, as you saw on the image, 3MI provides also unique observation for cloud retrieval and characterization. And more generally, this is the case for all the targets that we have on the Earth atmosphere system. Again, we have a strong heritage from the Parasol polder missions, which includes the aspect of the synergy with the other sensors, from the train especially. And we know that we have the ability to retrieve many parameters for aerosol and cloud. So typically the optical thickness, it could be the angstrom coefficient, the size of the particle, the albedo, the refractive index, the shape, the effective radius for clouds, some information about the vertical distribution or extent also, which is very important. And this is why also what we implement today on the operational processor is based on the retrieval that were developed in the previous years. So for the aerosol processor, we rely on the GRASP, so generalized retrieval of aerosol and surface properties. So the GRASP approach that will be presented by Oleg just after. And for the cloud retrieval, we also rely on the previous generation of cloud algorithm developed by Parol et al. And Riedi et al., for instance, and that will be presented by Jérôme in a second shot. So these two algorithms are under adaptation and implementation in the ground segment again for the need of the near real time, which is a very specific aspect that could be different sometimes to the purely scientific need. I remind that we have a specific care about the geometry of acquisition because it influences the performance of the product, and this is something we would like to better consider and document and also address in the future on this development. So this is for the level, that was for the day one product, so the product that will be available at the launch of the satellite. But in parallel, we try to prepare or to start the development of what we call the day two product, so the second generation of this product. So two major steps there. The first one will be first to improve the day one product that we will have, and on which we already know we can improve a couple of things. For example, for the aerosol, we can try to optimize the aerosol model itself. We can try to provision a more reliable estimation of the error. We can try to extend also to additional parameters. And for the cloud, we already know that we have to better use also to better exploit the multi-view, especially on the sphere domain, because it was not there on the Parasol previous mission. Also to try to revisit some aspect of the current algorithm to better tune to 3MI. So this is the first family of day two product that will simply improve the day one product. But we have also on the plan another family that is more ambitious and more exciting, probably. This is what we call the synergy with more generally the sensors we have on the platform. So the EPS-SG synergy that we can exploit for both aerosol and clouds. It's very exciting. So we can really have a multi-sensor approach for the aerosol. So adding on the 3MI what we can bring from the sensors. And same for the cloud, especially to have a better assessment of the vertical structure of the cloud, which is always very complex in general, especially with the synergy with the image. So we have already a list of ideas to explore there that will be probably mentioned by Jérôme and Oleg after. I take the opportunity to add a small note about an additional day one product that is not shown here because it's a level 3 product. In fact, it's not a level 2 product, but there's a product under preparation by the land SAF that will be the surface albedo and BRDF product. So it's under development. It is starting, and it will also rely probably mostly on what was done on polder. And this is typically the same approach. So to conclude on this future development for the future, I think we have a very, very good, exciting work to be done on what I call the unique observatory from the EPS-SG sensors. Because we have on the table not only the 3MI polarimeter, but what we can bring from the other sensors and what we call the hyper instrument. So it means that for the aerosol and clouds, we can really extend the list of parameters to be retrieved, or at least the performance we have. So this is very important. And you have here a view graph showing how the instrument can complement themselves. On the table, you see some properties, so spatial resolution, spectral band, spectral resolution. So you see that it is very different, so very complementary. And on the right, you see a view graph summarizing more or less all the information in terms of spectral resolution and so on. And showing also the way, in the case of aerosol, we can really try to use all the information from Sentinel-5, ISE, and Mesh to improve the aerosol retrieval, for instance, that we will derive from 3MI. So it will be a reinforced polarimeter, if you want, at the end. So now I thank you, and I give the floor to the scientists, so Oleg and Jerome. You have here a couple of bullets showing or recalling the way you can assess the product, so through EUMETSAT terrestrial and archiving, and also EUMETView. So thank you.
Thank you, Bertrand. Yeah, good overview talk, but we get to hear more details in the next talks on aerosol and clouds. But I think we can also take up some questions. Some of them were from yesterday. I think you wanted to answer them today, right? There were a couple of questions on the BRDF. I can bring it up, Oleg, Bertrand. Sorry. I'm stopping your screen sharing, yeah?
Yes. Oops.
It comes up, yeah. I think I have to just remove that float. Yeah.
So the first one, perhaps?
First one, given the 3MI characteristics, which BRDF model is EUMETSAT's distinct? Yeah, please.
So I guess the question there is related to the surface BRDF and not the atmospheric one. So for the surface BRDF, as I said, it is under development. So I think we cannot describe exactly today what it will be. But it is for sure the 3MI measurement will be able to feed something very similar to what was done on Polder. So I guess roughly model will be fully relevant for that. But I think it's not possible to provide a definitive answer to that today.
Mm-hmm. I think, what are the plans to continue the ice liquid cloud climatology provided by Polder?
Oh,
this one has been
related more to
this one has been answered by Jerome yesterday already. And the answer was yes.
I saw some reply, but I really do not know how to put the reply up here. But I think it's if Jerome, if you can care to summarize it.
Yeah, I answered.
I saw it, but
the answer is clearly that there is indeed a plan to continue this climatology. The cloud phase from polarization is indeed one of the main advantage of 3MI. So we want to continue this climatology from the 3 Polder mission, and that's clearly under the cloud phase from polarization is clearly a main ECV climate variable that we want to follow with 3MI. Yes.
Okay.
I think it will be partly addressed by what Jörg will describe after, and the reprocessing we have on the plan with the idea to create a climate time series.
It's another one. Are the day one land surface products from the LSSF those derived from GRASP, or is this example the Yves-Kevort's CISAR algorithm they use for Severi or something else? Yeah, please.
So, I don't know for now what are the last updates. I don't think it is neither GRASP nor CISAR, but I don't know. Maybe, I don't know if we have somebody from Landsaf online.
Let me just see.
Isabel is online, yes.
But as far as I know,
the problem is that if she has to speak, we have to let her, and if she raises her hand, speak.
Yeah, probably you shouldn't take my word for granted for this topic, but I've been in touch with someone from
hands
the
up.
LANSAF recently, and apparently they are developing their own algorithm for that.
So there's a message from Isabel in the
yes.
chat. Can I interrupt 1 minute? There's a message from Isabel. She says she doesn't have a microphone, but she writes here that the plan is to use an algorithm similar to that in operations in the LSSF to get albedo from severe inversion of kernel-based function to get the BRDF. I think what we can do is to answer this question, we go back, after the talk, after today's session, and get a reply from Isabel. I think that should be okay.
So the answer is something else.
It's like, what do you actually see now from my screen? Because
yeah, you.
now me. That's good. Okay, I go back to the share again because I
It
think
was not Slido we saw.
Yeah, but we will bring the slider. So this question we will take up, we will try to get it from Isabel later, or anyone from LANSAF. So I think, at what level is the synergy with other instruments expected? For example, will data from other instruments be put in the 3MI level 1C format?
This was also yesterday. Okay.
Yes, I think probably you mentioned that on the level 1C, we have partly this synergy because we have some information provided for VII. It is limited to VII and only a couple of bands. If you want the full synergy, using all the bands and everything, it will be done at the step of the level 2 retrieval for now.
Mm-hmm. Then how is the BRDF? I think someone tried to answer this question too. How is the BRDF characterization done for partly cloudy pixels? Can the cloud and surface BRDF be distinguished then? I think I saw some reply there. If you want to reply
yes,
now.
It's not an easy task, the partly cloudy pixel, especially for the BRDF effect, because we have to, when we are at the border of a cloud, we know that it's very difficult, depending on the view, to be sometimes partly, sometimes fully cloudy. So I would be very surprised that today we have a fully reliable way to retrieve the BRDF characterization for the surface when it is partly cloudy. So for me, it's more for the future, and it will not be for now, I think.
And I think this is for yesterday too, but will the 3 orbits of test data for VII overlap with those for 3MI? Thierry, if you can, we just can get rid of
Yes, they will fully overlap because the 3 orbits have been generated for all EPS-SG instruments, by the way, are the same orbit. And the two, from MetImage and 3MI have been generated by the same institute, that was the University of Lille. So they are fully consistent.
Good, great. Thanks. Bertrand, I think I stop sharing and we go to the next talk actually. That's from Oleg on the aerosol products. Oleg, can you share the screen? You are there. Hello.
Okay. Do you hear me?
Yes, we hear you.
Yeah. Okay. I shared my screen. Well, you don't need to see this, sorry.
No, this doesn't be. Again,
sorry. Yeah. Okay. Now it's better.
That looks good. Yeah. Okay. You start now. Okay.
Yeah. Okay. So I'll be introducing the developments behind aerosol level 2 3MI aerosol products. And here just quick introduction of the team working on that. First of all, of course, this is managerial team from EUMETSAT, and you see everyone's here. And also it's Laboratory of Atmospheric Optics from University of Lille. And we also have contribution of 2 software development company, GraspSS from France and CloudFreight GmbH from Austria. Well, this is just quick reminder, which probably is not needed, what kind of data 3MI will provide. Well, basically here I wanted to outline that the data will be have pretty good coverage with swath 2200 kilometers, and it will be with global coverage every 2 days at least, and it will make measurements in visible and shortwave infrared at up to 14 directions with spatial resolution about 4 kilometers. So it's very rich data. And the first data would be registered as geolocated stocks vector parameters, and then they will be at level 1B, and then they will be reprocessed and transferred to level 1C with geoprojected data, and which also will include some 6 pixel information from MetImage. And at the end, the retrieval will be done and it kind of latitude, longitude fixed grid, where all data at all direction, all channels, and with extra information will be at each pixel, and the processing for level 2 will be done for this data. As already said by Bertrand, at the moment it was decided that aerosol day 1 plus near real-time retrieval supposed to be done using simultaneous aerosol and surface retrieval, and GRASP algorithm was chosen for that. Here you could see short introduction to this algorithm. It stands like generalized retrieval of aerosol and surface properties. Well, it's based on the earlier developments which done for aeronet observation, ground-based observation. Many similar principles were adopted, and we developed quite efficient method which can be applied for satellite data, and it's been applied for several satellite database successfully. And what particularly important for FreeMI, it was successfully applied for Polder, predecessor of FreeMI. And as I will try to show you, it seems like GRASP respond to many expectations which for algorithm for such rich data as those from FreeMI. And actually expectation from FreeMI data pretty high. And here I just wanted to mention that, for example, several IPSS reports, and here I'm referring to one from 2013, mentions that main uncertainty, or at least one of most serious uncertainties in evaluation climate change, related to uncertainties with aerosol. And therefore, in order to reduce these uncertainties, we need to understand and get more detailed properties about aerosol particles. And actually, until now, these kind of details, for example, not only aerosol optical depth, which tells about amount and aerosol, but also information about size and composition and absorption of aerosol, could be provided only locally from such observation as those from aeronets and photometers. And now, having multi-angular polarimeter in space as polarimeter, we expect that somewhat comparable information, detailed information about aerosol, can be provided globally. And thinking that FreeMI polarimeters should present for more than a decade in the space, it will be quite useful and interesting climate record. And this is only climate application, but generally all those details about aerosol are needed for many other applications, for example, as those health related or application related with pollution. Now, Bertrand already mentioned that actually, looking at observation of multi-angular polarimeters, we have pretty high confidence that this information should provide detailed retrieval of aerosol. And here it's just a little bit different view on the same aspects. Specifically, I wanted to show you that the scattering of aerosol is determined by angular dependence of scattering matrix, which has 6 elements. Even without going to detail of this theory, on the left side you could see that once we look at a single view radiometer measurements as those, for example, from MODIS, basically regarding angular information, we have only one point. Of course, we have spectral value of this point regarding intensity. Now, if we look at polarimeters, such as free MI, evidently we see that we observe this phase function, first element of scattering matrix, in pretty wide angular range. And in addition, we observe also degree of linear polarization in the same angular range. And we have this spectrally. So information much more significant. And if we also look at the studies, how the elements of phase matrix depend on the properties, we see that this kind of measurements much more sensitive to the detailed properties of aerosol, not only amount, but also what kind of particle shape, nature, and sizes we have in the atmosphere. And this is just a quick illustration, for example, how grasp retrieval look like once the algorithm applied to polder data. And here you could see, like, if you see in the middle, we can look at aerosol optical thickness, and basically this high red spot shows you the high concentration of aerosol over Africa. That's generally what we can get also from MODIS-like observation normally, and we are accustomed to that. But on the left side, we see extra parameter. For example, on upper part, we can see angstrom exponent, and the higher value of angstrom exponent, smaller particles, the lower, larger particles. And you could see that over Sahara particles are larger, and on the south of Africa, they are smaller. And on the lower panel of the right side, you could see also single scattering albedo. This parameter characterize aerosol absorption. Closer to 1, it's less absorbing particle, and when it's smaller than 1, it's characterize ability of particles to absorb. And you could see that on the south of Africa, particles are much more absorbing. So they are small and absorbing, and that's related to smoke. Over Sahara, here on this image, they are large and non-absorbing. That's actually properties of dust. This is a kind of quick ideas how we get more detailed properties from multi-angle polarimetric observation. But at the same time, I wanted to outline that, I wanted kind of introduce you to different aspects which we had to face in developing aerosol retrieval algorithm for multi-angular polarimeter. Like you heard already from Bertrand's presentation and from what I showed you before, and many of you are good specialists in aerosol retrieval, we expect a lot of improvements from multi-angular polarimetric observation, and we expect a lot of advantages of this kind of measurements. On the left part of my view graph, you could see them align, and I already talked about that. But the practice shows that retrieval also brings number of challenges, which is somewhere quite well understandable. For example, to treat more complex data, evidently we need more complex algorithm. For example, simple algorithm rely on lookup tables may not work. We need to run radiative transfer line, and that takes time. So generally the algorithm become much more time consuming, and that can become an issue. And additionally, once we have very sensitive data to aerosol, we also need to think of many more aspects than we treat data less sensitive. We need to make many assumptions, and behind each assumption can be some challenges and errors. So all this need to be addressed, and at the end we have kind of compromises, balances between challenges and advantages. And why I'm talking about that? Because FreeMi is not first sensor. There was, for example, quite long record from Polder Parasol, and there was number of concerns that we have measurements, but we don't always see the advantages that we expect. And that was one of the main challenges in our developments of retrieval algorithm for FreeMi, well, and as well as Polder. And here I want to show you that with our algorithm grasp, it seems like being able to address most of those concerns, or at least we will placed our effort in this regards. Here, this is just quick illustration that first of all, of course, we adapted our GRASP algorithm, which was already working well for Polder, predecessor of FreeMI. That means we took a configuration of FreeMI observation, like changed spectral channels and geometrical configuration and so on. And we tested our algorithm pretty extensively. Also thinking of looking at those expected challenges. One of them, for example, speed of calculation. And here you could see the table, like we have different configuration of algorithm, and we tried to test on the simulated data the speed. And we found that for all configuration but one, actually this configuration was not most efficient. We are able to process one orbit of FreeMI data with pretty modest computer resources at the order of time of 12 to 15 minutes and even faster now. So the time is not a problem. And on the left side, you also could see that, well, in principle, GRASP is very flexible in using different a priori information. And we adapted its structure to handle near real-time observation, where we invert only one orbit at the time, and we use a priori constraint based on previous retrievals for surface retrieval. For example, for Polder, we don't do like this. We invert long record of the data at the same time. But all our tests shows that this adapted configuration should work well. But this theoretical test and kind of numerical test. But now let's, like I said, all compromises need to be tested with the outcome of actual results. And one of the main results of GRASP application is successful application of this and successful generation of aerosol product from Polder data. For example, Polder, 9 years of records of Polder parasol. And here you could see just, well, data from winter 2009. As you could see from these globes that we could retrieve optical thickness and other parameters like Angstrom exponent, single scattering albedo, and even some scale height parameter. And here we also provide many more other aerosol parameters that's interesting. But one of most important features of GRASP is that we try not to over-constrain our retrieval, in the sense that we want that retrieval is driven mostly by information into observation, but not as little as possible in our assumption. How we achieve that? For example, we use globally the same initial guess for aerosol. We also use globally the same set of a priori constraints. We don't use locally specific assumption. We work on the natural spatial resolution, which was 6 kilometers for polar aerosol and 4 kilometers for FreeMI. And we retrieve surface simultaneously with aerosol, which is very important, especially for getting aerosol over bright land surfaces. We also provide, of course, surface product, which is, as already was said by Bertrand, will not be used as operational product, but probably it will also provide some information for comparing with operational product. But let's talk about aerosol. Basically, we processed parasol data several times. We have several products. And that means speed is, again, confirmation that speed of algorithm is sufficient. And these products were analyzed in a number of papers. Here I mentioned several of them. You can have a look. But basically, the conclusion of practically all papers, or most of them, that we, with this data, demonstrate that we kind of satisfying the expectation. First of all, if we comparing, okay, I'm again talking about MODIS because this is kind of reference data set, which widely used. Well, if we compare to MODIS like imagers, what our product, what we see, and what the results of this paper shows that generally such basic properties as aerosol amount is seems like from polarimeter of Polder is at least a similar quality of as MODIS and even better sometimes, but there also we need to look on resolution and other factors. But what's most important, the detailed properties like information about size, like Angstrom exponent or concentration of fine and coarse particles over ocean, even in the simplest case, from polarimetry generally have higher quality. But what most important, that there is some information, again, the like amount of large and small particles, fine and coarse particles over land, and such new parameters as single scattering albedo or aerosol optical depth of absorption are available basically only from polarimetry. There is also another finding, maybe, which is shows that I mean, which is consonant with my previous mention of challenges. Actually, we found that algorithms are complex and sometimes they need tuning, especially if, and tuning can be different for different products. And I will tell you a bit more specifically what we, how it's appear and what we do about that. For example, well, as long as we know, I mean, since we know that multi-angular polarimetric observations so rich in information, there is temptation to use very complex aerosol model. And in GRASP, we use, for example, aerosol model here on the right, pretty complex, where we retrieve quite detailed aerosol size distribution and spectral dependence of complex refractive index together with BRDF and BPDF. That was our initial attempt. And also we assume particle can be mixture of spherical and non-spherical particles. But also we can see that a simplified model, when we do not retrieve size distribution complex refractive index separately, but rather we can see the aerosol as external mixture of components, aerosol components, which is somewhat similar what been done in MODIS. However, of course, we have a continuous retrieval. So as a result, we can retrieve either a lot aerosol parameters from one pixel, like 23, let's say. In the bottom you could see, or much less parameters, 6. And of course you would be interested to know why we do such different approaches. Apparently this is actually results from our paper from Chen Chen from our team, where he analyzed several data product, GRASP product from Polder, and we also compared with 3 different MODIS products, and we try to understand how actually we do, how the Polder data compare to this widely used MODIS data. And on the top you could see 3 different products from Polder. 2 first products used were developed using this complex aerosol model. This is something we started from. But the problem is we identified that we actually, for small IOD, we had a bias for both cases. Even one supposed to be more optimized than other one. And bias quite essential, 0.06. And while we try to explore different versions, we applied this more constrained aerosol model. We got that we removed this bias completely, and we also improved correlation and other parameters like G-cost fraction. And if you compare these two to the all parameters derived for the same database, defined for the same database, it's 1 year for 2008 for 4 even different MODIS data. It seems like this GRASP models approach provided the best metrics, or at least comparable, for aerosol optical thickness. At the same time, if you look at more detailed properties, like Angstrom exponent, here you could see both land and ocean. Apparently, some more complex models which we use provides a bit better some parameters for over ocean and over land, but for both more complex and simpler approach from grass polder, we still get a kind of better product compared to the Angstrom exponent derived over ocean from either polder operation, which is heritage algorithm from polder, or from MODIS dark target. But if you look over land, actually, as you could see, basically, well, results for both grass polder products are significantly better, although the complex model provides somewhat better parameters. But in any case, they're significantly more meaningful than those from MODIS and over bright land size surfaces. And in addition, we can provide many other parameters, and here I just will show only most kind of elaborated single scattering albedo, which characterize absorption, which both over land and ocean for two different wavelengths. And as you can see, we have a pretty good correlation with root mean square about 0.05, which IRONET couldn't expect from 0.03, so it's a bit lower quality, but nonetheless, based on our validation, especially when optical thickness quite significant or moderate, we provide this property quite well. And I also wanted to say, as Bertrand mentioned, that we have kind of version of algorithm of different maturity. One which will be applied for level 1, and then there is level 2 processing, and where different synergies can be used and so on. So we are thinking also about some possibly more interesting and more advanced but more challenging products. For example, for many applications like derivation of air quality, particular method 2.5 or 10 is very interesting, and it's kind of grail for the aerosol retrieval. So now we are also looking, can we actually do something in that direction from free MI or multi-angle or other multi-angle parametric observation. And actually there is pretty good, we think that these data provide pretty good basis for this kind of retrieval. First of all, in order to separate particles by size, we retrieve size distribution, so we can have discrimination of sizes. We also have information about refractive index that will let us to judge about water fraction, so we can kind of model particle drying. And most importantly, polarimetric data have sensitivity to the vertical distribution of aerosol due to polarimetric measurements. So we retrieve scale height, and therefore we can meaningfully project amount of, or at least try to project amount of aerosol next to ground. And we now looking at this data, and of course if we can make other coincidence synergetic data, this approach can be even improved. But for now we try to use only like polder, like of remind like data from polder, and here you could see like we generated, for example, PM2.5 map of average values of PM2.5 for 2008, and you can see how it looks like. We use this our simpler approach, models, although we did it for different type. And as you can see, all visible air pollution hotspots are obvious here. We see biomass burning, we see desert dust, we see over Sahara, over Taklamakan Desert, we see this in the Ghanaian Valley, we see a lot of pollution over China, we see Russian fires, and over ocean, evidently we see that it's not so much PM2.5, although nobody have measurements over ocean, but at least first results look reasonable. We also calculated PM10, but PM10 include PM2.5, and here I just show you like ratio PM2.5 to PM10, and as you could see, for example, it's evidently that for the high for high biomass burning event over South Africa, the contribution PM2.5 dominates, while for areas where we have dust, it's dominated by coarse particles. So, and of course, these are preliminary results. We have some validation on certain sites, but we plan to do more and probably to do more tuning. But these preliminary results quite interesting, and this is just I wanted to show you kind of work in progress in the direction of looking for more advanced aerosol product for FreeMy sensors and other polarimeters. And here's my conclusion. Well, basically, we have quite solid results that we have algorithm, which is where like FreeMy grasp, I would say, where we overcome number of challenges. For example, speed of retrieval is not issue. We evidently provide more aerosol, more detailed aerosol information, including information about aerosol absorption and many other parameters which can be used to identify aerosol type. And we retrieve also surface properties, which is not a part of aerosol product, but nonetheless can be interesting addition. And based on our estimation, the accuracy of all retrieval retrieved aerosol parameters can be compared to what we have now, can be retained and even increased with FreeMy product once it's become available. Well, like I mentioned, we have I have a lot of optimistic messages, but also acknowledge some challenges. For example, we find that providing all parameters with high accuracy is challenging in single approach. I'm not saying it's impossible, so we are now looking for potential optimization. And also, of course, we still have a lot of potential, and we think that our approach can be tuned in future activities like those which Bertrand mentioned, going from level 1 to day 1 to day 2, sorry, not level, day 1 to day 2 and further. And I think we can provide even better parameters. And as a perspective, I think analysis of future FreeMy aerosol products from polarimetric observation should bring important correction about aerosol climatology and maybe other finding. And again, we think that FreeMy data should bring qualitatively a superior insight about distribution of aerosol product properties. And I'm done. Thank you.
Thanks, Oleg. Very interesting talk on aerosols and the challenges that you have had. I think I will bring up some of the questions if they are. Just have a look.
Shall I stop?
Yeah, I think it will be better than I.
Okay.
Do you see the questions actually?
Yeah.
I just highlight. I think that's a general question, right? How do you plan to assess the end quality of the level 2 only with RTM and ground truth? Or you plan to open comparisons with competitive algorithms? Maybe you want to say.
Sorry.
Bertrand, okay. Mm-hmm.
Yes, I can answer on general approach for aerosol and clouds. I think the approach is we rely on different aspects. First, space-based comparison. So we will compare the data to other reference sensors. It could be MODIS, for example, VIRS. It could be other sensors we have in EUMETSAT because we want to check the consistency between all our sensors. So for clouds, it will be METEOSAT, for example. For aerosol, it will be Sentinel-3 or PMAP. So space-based. Ground-based, for sure. We will rely on in-situ measurement. Aeronet is very famous for the aerosol. We cannot avoid it. But also other stations for the clouds. Model-based, we have also potentially an approach to compare this data to what is produced by the model. It's also useful information to detect some bias, for example. It's very important. And it is true that we have also an additional option, that is to try to compare to alternative algorithm. It's on the table. We don't have a very clear plan for that, but this is something we do in general. We create what we call the validation team, on which we invite people, or we support people sometimes to work on an alternative retrieval that is supposed to be good also, with the idea to compare and to detect anomalies potentially. So we have different approach.
And Bertrand, can I add a little bit here? Maybe some information regarding comparison with competitive algorithm. We probably didn't inform you yet, but we have a joint project with Olta Hazelkamp from SRON. Once we asked this project from ESA, and it was got granted. And in frame of this project, we actually compare two our approaches and results from of application to competitive algorithm to Polder. So it's not really to FreeMI, but to Polder. But nonetheless, we expect to get a quite interesting insight how different algorithms perform, where they agree, disagree, and how to improve both algorithms. Certainly, you and EUMETSAT will be informed of outcome of this project, and if something useful found, it will be also used for improving FreeMI grasp algorithm.
Thanks, Oleg. I think I take some, maybe this question. Anthropogenic PM 2.5 is often distributed close to the surface and often high SSA single scattering, but can polarimetry help to resolve the weak signals from PM 2.5?
Well, actually, in my presentation, as you could see, I touched a little bit, and in short answer, I cannot go much more far, but at least I can say that polarimetric data certainly improve sensitivity to this weak signal from PM 2.5. First, because there is some sensitivity to vertical distribution of aerosol, because a very strong polarimetric signal comes from molecular scattering, which is vertically quite stable, and appearance of aerosol at different level is different. Also, we have sensitivity to refractive index that's help us to mimic drying effect, and we also have sensitivity to size. So I think we have better sensitivity, and polarimetry should help resolve that issue. If it will provide fully credible product, we need to see, but certainly some progress can be done.
Okay, thanks, Oleg. I think we'll take one more question. This one, not the test data, because that's for maybe level 1, and we take that up in the end or later offline. I think we need to look at this. Are there, and then I think I propose we take a break, because I think we've been here sitting long. Are there any plans for comparison of 3MI and EarthCare atmospheric LiDAR data products once both are in orbits?
So yes, it is clearly on the list of the what I mentioned before about the space-based comparison. So yes, definitively we have the LiDAR, the space LiDAR on the list that we will use if available at the time of the validation. Yes.
Okay, thanks. I think I would take one more question, then we take a break. Sorry. A further comment about aerosol remote sensing comparisons around the same time of 3MI launch. Okay, that's a comment. NASA space mission with 2 polarimeters on board will be launched. I think that's a comment.
Yes, same answer. Again, we will use all the space information that are mature and relevant for the comparison, because as it was explained by Oleg about the retrieval, about the space data, this is the same. And when you try to cross different source of data, you learn a lot. If you have indeed the good maturity of the product. If it's not the case, that's another story. But so if we can rely on the pace measurement, we will for sure include such data on the comparison.
Okay, I think we definitely take a break now. Before that, just let me remind you that we have also a survey for today's session. I mean, we had one for yesterday's, but we want to get your opinion on how you liked today's session. So Stefan will pop up on the chat the link to the poll. So please be kind enough to express your opinions there. And then we discuss some objective multiple choice as well as text questions. And then we come back in 5 minutes. So that's at 15:05 CEST. So the time here in 5 minutes. See you all. Take a break. Have a drink and then come back. Welcome back, everyone. Happy to see that you're all back. We have about 100 plus participants right now. So, Jerome, I think you can start your presentation now.
Okay, is that okay?
Yes, that looks okay, Jerome. Please.
Okay, so I'll try to do a brief overview of the cloud properties from 3MI, and of course, this presentation is on behalf of a big team at LOR, some partners from the EGEOS company, and postdocs and colleagues from abroad. I'd like to acknowledge also the 3MI team members, and obviously all the contributors to the 3 polar missions that were the precursors for 3MI. As it was discussed previously, I think I messed up. The launch date is not 2021, but 2024, obviously. And even though 3MI is a dedicated aerosol mission, initially it offers lots of capabilities for cloud remote sensing. And 3MI actually builds on the Polder Modis heritage for the retrieval of cloud properties. And what I want to discuss briefly today is how the 3MI cloud product could be actually helpful in addition to the heritage other sensors that were dedicated to clouds, and why is 3MI innovative in that sense. As Bertrand and Thierry and Oleg have already mentioned, there's a very high information content from 3MI. There's more than 500 individual agencies available. And that actually can be used to account for the cloud vertical structure, because the spectrally varying weighting functions of different channels actually carry information from the vertical structure of clouds. We do have a 2-step approach for the operational processing of cloud product. The first one is the day one near real-time algorithm that's going to infer traditional cloud parameters using plain parallel homogeneous assumption, just to make sure that the algorithm are working in a continuity mode with previous missions. And also we have a day 2 algorithm that's still under development, where we're going to use the a priori information from day 1 retrievals to constrain a more realistic cloud profile. And to do that development, we're relying on 2 flavors of highly realistic synthetic test data. The first one is assuming homogeneous single layer, single phase clouds. This is what we call the simplified physics. And then we've got the enhanced complexity with mixed phase, full vertical profile description, aerosol mixed in the scene, etc., etc. 3MI, first of all, has a few assets compared to other existing operational cloud mission. First of all, thanks to Polder, it was demonstrated that 3MI will be useful for aerosol remote sensing above clouds, which was kind of unique. 3MI also offers a unique unambiguous thermodynamic phase determination technique, and we can use that as a standard to validate other geostationary product or other meteorological product. And of course, continue the polar cloud phase climatology as it was mentioned before. Also, thanks to the polarization, we have information on the cloud effective radius and effective variance. And it's not only thanks to spectral information, but because of the polarization, we do have more information on the size distribution, on the width of the size distribution, and that could be particularly helpful to understand processes and constrain better the cloud droplet number concentration, for instance. The cloud geometrical thickness also can be retrieved from the oxygen A band and the multi-angle oxygen A band observation coupled with the ray scattering product. The 3MI product are going to be multi-angle by design, and it was demonstrated from Polder that this product can be used to create ADMs. And so one of the contribution of 3MI for this mission is that it can be used for flux and radiative budget calculation, and also help in the intercalibration of sensors. And of course, the scene polarization, that's not typical for clouds, but the polarization characterization is going to be useful for calibration and correction for the sensors. Now, these are the list of what we call the main cloud properties, which are going to be derived NRT as day one product, the cloud phase from the multi-angle polarization and combination of the visible and near infrared and short-wave infrared channels. So we are leveraging on the Polder Modis heritage for that algorithm. The cloud top pressure is going to be retrieved from ray scattering in addition to the oxygen A band. The cloud geometrical thickness also and the multi-layer detection is going to be possible from oxygen A band differential absorption. The cloud optical thickness is going to be retrieved under different directions, providing better albedo and directional information for that product. And the cloud particle size, which is traditionally available from short-wave infrared using traditional Nakajiba and King kind of like algorithm, is also again going to be retrieved from multi-angle polarization. And compared to Polder, we've got the big advantage of having longer wavelength. So we expect more information. And all these information are going to provide cloud properties that are essentially sensitive to different parts of the cloud, as was shown by Platnik in 2000. So we hope to combine all this information to better describe the vertical profile of clouds. This is just an illustration of the very particular capability of 3MI, the polarization measurements, which allow the observation of rainbow for liquid clouds, and that's a very unique feature of the 3MI. Combined with the Modis, Polder and Modis were used to derive an improved cloud phase, because all these channels carry different information on cloud phase. They sample different depth in the cloud. So the Polder Modis algorithm is used as precursor for 3MI. And of course, we can think about adding VII thermal channels to have a full replication of the Polder Modis algorithm. The main advantage here is that we're going to have the multi-angle information in the short-wave infrared as well for Polder. This is an example of the effective radius and variance retrieved from polarization. And again, one of the big advantages of this technique is that it's mostly insensitive to cloud albedo. And so we can derive reliable information on cloud microphysics in regions where traditionally the other sensors are struggling a little bit due to the bright surface. And for instance, the Arctic and Antarctica region are obviously of interest for what we can do with 3MI. Now, the reason we're interested in this detailed microphysics is of course because in a meteorological context, we want to be able to address the process studies. And this is, I think, one of the key contribution of 3MI for clouds is it's going to provide more information on the vertical profile of cloud particles, on particle size distribution, and that's going to be useful for characterizing processes ongoing in clouds, coalescence, cloud glaciation, understanding at what type of, what's the limit of the size of droplets where we can reach glaciation for different situation, meteorological conditions. So all of these studies are obviously of interest and will be possible from 3MI. The strategy we're using for algorithm development is mostly based at this stage on the synthetic test data that we are creating. And we start by having a very highly realistic description of the atmosphere. And we run RTMs simulation to create the level 1B sensor geometry data from which the level 1C can be generated at EUMETSAT. And we can also compute directly what we call the perfect level 1C, which is basically a multi-angle simulation for a given pixel. And these two sets of level 1C can actually be used to run the processing software and do the retrieval and also assess the impact of channel registration and how the noise of the registration in polarization and the noise of registration at multi-angle steps actually impact the retrieval. So this is actually extensively used to test the algorithm. Now, what is a realistic cloud vertical description, you may ask, for the simulation? We are using the ECMWF ice water content and liquid water content profile to prescribe the guidelines of vertical distribution of water in the atmosphere. And then we are varying the particle size from cloud top to cloud bottom. And the cloud top altitude, the COT, and effective radius information are prescribed from coincident AVHR retrieval that we got from Andy Heidinger, but we could basically use anything. And now the next question is, once you've set up this complex profile of cloud and water cloud in the atmosphere, what is the phase when you have multi-layer and multi-phase situation? What is your phase? Where is the cloud top in that situation? How can we provide meaningful information for the numbers for various particle size? And what's the relation between the extension, the water content, the particle size? So all these questions have to be answered, because when you do your retrieval, you get a single number. And when you do a single layer cloud properties retrieval, of course, you're going to get an answer that's a radiative average of some sort for this very complex profile. But that's what we input in the test data, and then we can run the algorithm. This is just an example of the cloud mask retrieved. The center image is the assumed AVHR input, and on the left side you've got the simple test data, so single layer test data, and then retrieved cloud mask, and on the right side is the full physics. You can see we're getting a very good match, at least a very good score for the cloud detection, which is not the most difficult part, obviously. For the cloud phase, as long as we assume a single phase, again, we are doing a very good job at detecting the ice and liquid phase for the clouds. But that's mainly because the algorithm is working on an idealized test data. And when you switch to full physics test data, you've got this occurrence of liquid and ice in the atmosphere, and that's reflected in the signal. So you have to decide what's your, when you want to turn this information, this complex information, into a binary mask, you have to decide at which part of the cloud you're looking at. And so the decision we made for this comparison, we know that the polarization is mostly sensitive to the cloud top. So what we did is the input ECMWF mask is derived from the dominant phase in the ECMWF profile down to an optical depth of 3. So that's roughly the fraction of the upper part of the cloud that we are sensitive to from polarization and short infrared bands. And again, you can see the scores are doing pretty good job at detecting the cloud phase for that top layer. Of course, if you want to know what's below that, you would need other sensors, and that's part of the synergies that we expect from EPS-SG. Another example of the cloud detection, multi-layer detection product, when we apply the algorithm on the simple phase, on the simple test data, sorry, obviously we retrieve very little multi-layer situation, that because the assumption was basically that it's a single layer phase, single layer cloud, so that's good news. We are not detecting multi-layer situation when we simulate single layer phase, single layer clouds, sorry. And when we assume the full vertical profile description, that's when we start to see a lot of variability in the multi-layer situation. And of course, we have to understand. So we're running more simulation now to understand exactly in which condition the multi-layer detection is going to detect indeed multi-layer clouds. Cloud optical thickness, that's a fairly traditional product. Again, it's going to be available at multi-angle. So this is going to be helpful to characterize the 3D effect of clouds and all these effects that can change the radiation budget of clouds. It's just a comparison for the liquid clouds and ice clouds retrieval. There's obviously some noise in the retrieval, but basically we've got a very good correlation between the assumed optical thickness and retrieved optical thickness for both liquid and ice clouds. This is the particle size, effective radius against validation. I want to mention that this is the bispectral retrieval using the short-range infrared and near-infrared retrieval. It's not the polarization-based retrieval here. I want to mention also one advantage of using this simulated data is as Bertrand mentioned, the information content of 3MI is going to vary depending on which side of the orbit and what angles are actually available. So it's really good to do these tests for realistic orbits. And of course, we want to do more orbits, more test data to evaluate what's the performance of the algorithm in realistic conditions, not just the idealized case. Finally, the cloud top height from oxygen A band, again, comparison between the simple physics and the full physics with ECMWF inputs. And you can see that the ECMWF, here we've decided that the cloud top is at an optical depth of 1 below the, so we're basically integrating the ECMWF extension profile down to an optical depth of 1, and that's where we decide the cloud top is from the input, and we compare that to the retrieval, and you can see a fairly good match between the two. These are the comparison for both liquid and ice clouds again. Obviously, it's a little bit more complex with ice clouds, which are more transmissive and geometrically more extended. But we want to improve that through the day 2 full profile retrieval. This is going to be the geometrical thickness again. I'm not going too much into details of that. Now, what's the approach for the advanced retrieval? So once we've got this first estimate for cloud top pressure, the traditional parameters, cloud top pressure, cloud geometrical thickness, cloud optical thickness, and particle size, we've got a first a priori for what the cloud is, and the next step is to optimize all the parameters describing the cloud profile to be able to match all the spectral information. And again, there's a lot of information and spectral and multi-angle information from 3MI. So we start from these parameters, and then we make a fairly strong assumption that the cloud extension the vertical profile of water content or ice content is like a triangle. And the idea is that thanks to the polarization that's mostly sensitive to cloud top and the other channels that are providing information deeper into the clouds, we can try to constrain this triangle shape. Of course, we're not claiming that this is going to be fully realistic, but at least this triangle and this profile is going to be a consistent radiative representation of the cloud that is able to match and to match all the observation, hopefully from 3MI. So in addition to all these physical parameters, the cloud top temperature, cloud top altitude, the geometrical thickness, etc., we also have the shape of this profile described by a parameter P, describing where the maximum of the triangle stands in the atmosphere. And this is an example of just one case that we're doing. The blue curves are the actual cloud profile that we set in the input test data from ECMWF. The first guess is what we retrieved from the single layer retrieval, and so we set these variables from the first day one output, and the green curves is the the parameters that after optimization, after free iteration. And again, as you can see, we are not completely describing the profile, but the green profile that we're seeing for the particle size actually seems to make sense. And even if it's not perfect, it's going to be still a lot better than claiming that the cloud is fully homogeneous. Now, just to briefly conclude this talk, I want to address just a few science questions and an application for 3MI. And very briefly, one of the interests of 3MI is in this capability to provide more information on cloud microphysics. And we're interested in cloud microphysics because having a good information on the cloud phase is essential to understand how the liquid to ice transition occurs and how the precipitation can be started from glaciation or from coalescence. And there were multiple papers based on Polder and Modi's data where we studied the liquid to ice transition for different meteorological conditions, which I think are going to be of great interest for meteorological application. And not only the meteorological conditions actually impact this process, but it was also demonstrated that the aerosol can impact the way the phase is changing in clouds. And again, there were a couple of papers where we studied from Polder and Modis the impact of aerosol and long-range transport pollution on cloud microphysics in the Arctic. And of course, since 3MI is a mission dedicated to aerosol, it makes totally perfect sense to use that instrument to study cloud and aerosol interactions. 3MI is not going to be able to provide all information, and if we want more information on clouds, of course, we're going to use METIMAGE and the thermal infrared channels. We may want to use YASI for the ice clouds vertical profile. Sentinel-5 also is going to be very useful for aerosol characterization. So this entire set of instruments is going to be extremely useful to understand the processes of aerosol and cloud interaction. Just to conclude the take-home messages I have for today, 3MI, first of all, is going to bring a whole new mission to the atmosphere, new vision to the atmosphere, polarization and multi-angle. It has a lot of heritage from Polder, of course, but it's the first time it's available from an operational mission. And these data are fairly complex, so it definitely requires users training and tools tailored for such observation. It's a first dedicated multi-angle polarimetric mission in such a context. But it opens path for long-term monitoring of ECV, and I guess Jörg is going to talk more about that. And this information are going to bridge the gap needed for long-term monitoring of cloud and aerosol process studies Of course, there are other missions currently ongoing. There's the Japanese SGLI mission, the Chinese at the DPC, and PACE is going to come. So all these parametric missions are slowly filling the gap for the detailed, the need for detailed information on clouds, microphysics, and aerosols. It will advance our capability to observe and model aerosol above clouds. This is an obvious potential for assimilation. And it's going to be fairly unique instrument for cloud microphysics detailed characterization, and probably a first attempt to derive vertical cloud profile from visible passive measurements. And of course, there's lots of opportunities with synergies with other instruments. So lots of work to do, and we of course welcome intercomparison of sensors and intercomparison of different algorithms. I'll be most happy to help anyone willing to compare the retrieval algorithm and provide guidance for the usage of test data if someone wants to dig into that. And with that, I will take your questions.
Thanks, Jerome. Your presentation didn't take too long as you thought. I mean, it was within time, maybe 5 minutes more, but that's okay. We can tolerate that. But I also liked no, that's okay. I also liked the way you posed the science questions, because I just have to mention that this is one of the intention that we have for organizing this sort of webinars, actually, because we want to stimulate scientific developments to make the best use of this data for the applications. So I think that was a good way to pose it there. Let me see what we have, okay? The questions we have. Still have to learn how to do this quickly. Oops, that's the poll. Okay, it's a bit slow too. So I think this is a test data. I think we will take that up later. I think I'll take some specific questions that were addressed to you. Jerome, cloud geometrical thickness is even possible at 3MI spectral resolution without multi-view in the oxygen A band. Those day 2 results, this one, I think, the first question, those day 2 results for radius profiles with or without 3MI shortwave infrared channels, and why not using aerosol retrievals at the cloud base to improve those radius profile retrievals? So that's 3 questions in one.
For the first one, of course, you have information from oxygen A-band, even if in a single view observation. But when you do the geometrical thickness, the better you know the cloud top, the more information goes into the oxygen A-band. So adding this multi-angle measurements and coupled with the ray scattering observation, there's just more information, and it's probably going to provide better retrieval. But technically speaking, if you have the right signal to noise ratio and the right bands, indeed you could use a single view oxygen band. I think that's what they're using for VII, by the way. I think the advantage of 3MI is this. The design of the instrument makes it very sensitive to some stray light or noise, but the noise is being killed by this additional information. That's basically the trade-off we have. We have probably a less well characterized instrument in absolute calibration on a pixel by pixel basis. But this additional information from the multi-angle view are actually balancing positively this problem. The day 2 results for radius profile, they were using the 3MI SWOT channels indeed. And why not using aerosol retrievals of cloud-based to improve those radius profile? Yeah, why not? That's a good question. It's not what we are doing now, but that might be, yeah. I guess the question is about the constraining the cloud droplet number constraint, and yeah, that's probably a good idea. It could be something we investigate in the future.
Take the next question. What's the ice cloud particle model used in the cloud optical depth, cloud effective radius?
So here we're using, and that's what we're using in the test data uses the BOEM and Pingyang and BOEM cloud properties database. I think for the retrieval I've shown, we were just using for the single layer retrieval, we were just using the IHM model that was developed for Polder. So we were not exactly using the same model for the retrieval as for the simulation. And again, the question is how that impacts the retrieval. So we want to study this. In the operational official product, we are going to use more advanced cloud models, cloud microphysics models, and probably the BOEM and Pingyang ice crystal models.
Okay. I think I saw maybe this one. Is there a plan to perform the stereoscopic cloud top height, cloud top wind retrievals from the free line?
I think that's going to be an interesting subject. The fact is that the free MI resolution is 4 kilometers, so we won't be able to get very highly detailed stereoscopic height retrieval. But it could be of interest to do that because, as it was mentioned yesterday, the level 1C processor for FreeMI actually allows to collocate multi-angle observation at the cloud altitude. So if we were able to use the stereoscopic retrieval from the level 1B to provide a sort of best estimate for the cloud top height, that could indeed be useful. I believe for the accuracy needed for cloud top height and top wind retrievals for meteorological application, I suspect FreeMI might be too coarse in resolution at this stage. We will have to see if we can combine this with VII, for instance. So probably the synergy with VII might be helpful if we're able to describe the subpixel variability.
Jerome, we take maybe a couple more questions and then.
Sure.
Maybe this one. For COT, the cloud optical, is it? No, cloud top, yeah.
For the COT retrieval, do you plan to include directional information? That's the one?
Mm-hmm.
Yeah. The directional information is going to be a product indeed, yeah. So it's not only the average COT across views. The average COT will be available, but also the multi-angle information. And when we talk about average COT, it may not be a full, just a plain average. For Polder, we were using a weighted average where we were using the most favorable geometries to gain more information on COT. So, for example, a significantly darker or nadir reflectivity other than use could potentially imply a fraction. Yeah, so that's this question is definitely part of the synergy with VII. How we're going to use the high resolution within each pixels to better describe the ADM that we're using to provide the average COT, for instance.
Okay, maybe take this one as well, yeah. Evaluation of the retrievals using the simulated data is great. Subpixel cloudiness or subpixel variation of cloud properties will be expected to be a major source of uncertainty at the 3MI resolution. Is that also evaluated with the simulated data? So
not yet, because the 3MI simulation have been done at 3MI resolution. There is an ongoing effort at ETHEROA to perform a set of test data for VII and 3MI directly from 3D Monte Carlo simulation. So we're gonna start doing full 3D Monte Carlo simulation for a limited set of scenes. But I guess the guy who's asking, or the guy or woman who's asking that question, probably knows that 3D effect can be a career-long effort to study. So initially, it's not the main question we're addressing, but it's definitely something we want to evaluate to understand how VII, especially how VII, can help in providing better radiatively equivalent optical thickness for the scene.
Okay, I give you a break and I ask Bertrand a question. Bertrand, you are here, right? It's about the validation team, validation question. The validation team exercises after a probe are often a pro bono activity, good for EUMETSAT, less good for the others. Would EUMETSAT be willing to trigger similar round robins, such as ESA did with the CCI initiative, that would engage more the community? Bertrand, would you like to answer that question?
Yes. So I think we have two major steps. The first step is to have our own assessment of the product before releasing the product to the users, even if it is in a preliminary release. We want to validate the product to be sure we don't distribute something completely useless. So we have in any case this in-house activity and perhaps relying on some partners for that. And then after, when we accept to distribute the data, we believe the maturity is at a good level for a first release. We create what we call a validation team that is also used by ESA. A validation team that is close to the project, and we can rely on it to have additional feedback simply for that. I don't see for sure we will play the party of potentially of a CCI exercise later, round robin, when it will be available. Well, we will think the 3MI data will be mature enough for that, because it's useless to do that if you don't think you have the good maturity. But it's not the thing we will put at the top of the list. For me, it's something that will come at the later stage when we think we are pretty okay for that.
Okay, Bertrand. I think we take the rest of the questions later, and yeah, I have to bring back my control.
And I tried to answer some questions in the chat as well.
Okay, when we compile the answers in the end, we can export those answers too, so that's fine. And one thing we can do now is that we take, before Jörg's talk, to take a 3 minutes break. So we come back at 15:44 in CEST, if that's fine. I think everyone needs to get a break.
Sorry for the exhaustion.
Yeah. Okay. Thanks, everyone. Be back in 3 minutes. Welcome back, everyone. Jörg, you can share your screen.
Yes, no.
Okay, good.
I'm here. I didn't miss the bus. So, computer is doing what I want.
That looks good, Jörg. So
should be there. Should I just start?
Yes, please go on.
I just need to relocate you all here. So, good afternoon. So this is the last talk in this very interesting webinar. I can only congratulate the speakers before me. It was very interesting for myself as well to learn much more about all these developments on 3MI. So I will touch base a little bit on data reprocessing support to climate research and services. And I think looking at the clock, I need to be quick. But nevertheless, I will try to run you through a little bit on the climate context. So Oleg has started that, but I probably have a few sentences to say. I really like to get to the long-term observation commitment. That's very important. A little bit on what is reprocessing actually doing, and a few examples from other instruments and products, so that those who are not really experienced with data reprocessing see what probably comes out of it. A little bit on the infrastructure evolution and how we plan to establish the reprocessing capabilities. So infrastructure, of course, is super important, particularly if you collect a lot of data. A little bit on future data exploitation, only one slide on the European Weather Cloud that probably forms an opportunity for many things that I even have heard today, and a little summary at the end. So I think many of you have seen this little illustration that was in Nature a couple of years ago, but I still think it's very applicable. So it just shows the importance of observation. So if the Earth is our patient and it would be in hospital, it would probably look a little bit like that, probably less messy. But we know that climate change is ongoing, and of course we need to measure what we can measure to really understand what's going on with the body Earth and the atmosphere above it. And that's still an ongoing thing, although we have learned a lot over the last few decades, but we still need to learn more about it. So looking at the IPCC report, and Oleg had a similar plot there, I just like to focus here on this third bar, the yellow one, where you see other anthropogenic forcings, which is the forcing through aerosol, but also to land use changes, which is connected in this chart. And of course, what we know about aerosols is that the radiative forcing from aerosols has always competing components. So there's a dominant cooling effect for most of the aerosols, and also through their cloud adjustment. So they change clouds, they change lifetime of clouds and other things. And this is also where the biggest uncertainty is. So the combination of having measurements where you can connect aerosol properties and cloud properties is actually a great thing that would allow progress, particularly in modeling and also in climate models and parameterizations from the measurements from 3MI using combined evaluations of the retrievals that Oleg and Jerome have actually talked about. And of course, this cooling is offset by absorption from black carbon in particular, black carbon aerosol. And that is also a feature of the 3MI, and that you have a handle on the absorption. And I think so in that sense, 3MI is really a super important instrument on climate. And I mean, what we know here, so they say in the IPCC, so there's high confidence that the total aerosol radiative forcing has counteracted the warming a little bit from the greenhouse gases. But this counteraction is smaller than they have reported in the AR4, and I haven't seen the plot in the AR6, so I'm really looking forward to that. So this is just a summary slide. I'll probably just skip it in the interest of time. So what we have heard from the presentations before, one thing I think Bertrand has said there, probably also yesterday, the good thing here is that the first operational dedicated aerosol mission with advanced cloud observing capabilities. And I'd just like to point you to the word operational, because that's very important, because this is the point where it's secured that you get more observations over time, and we'll probably get it even after the EPS-SG with the next program, so that we can really build a long series of data that support, of course, weather forecasts, but also climate data records. So the regular contribution that EUMETSAT does in the area of climate monitoring is, of course, that we have these long series, and we have that for many instruments. And we continuously improve and expand our portfolio, which you have just seen. 3MI is a very good example for the expansion of the portfolio of observations. And then we put this all in our super big archive that has tons of things. We also do historic data rescue. And then we normally work in reprocessing. And this will be probably also happening for 3MI on things like recalibration of the instrument. So we've seen there are many opportunities also to use different instruments to cross-calibrate. And I think we will see several variants of how to do that. And then for reprocessing, you can try those out, and you can actually choose them the best to go back and reprocess the time series to a kind of best product. And then we produce, of course, some geophysical parameters. Not all will be processed here at the EUMETSAT headquarters. And I think the SAPs will also contribute to this, as we have just seen from one intervention that Isabel made. Estimation of uncertainties is also interesting. And I think maybe some of the retrievals give us also a handle on some uncertainty estimates and gradients. Thierry can actually clarify that better. What we do about uncertainties was not here yesterday, so could not really listen to him. And then there's all the stuff on data access and cooperation with users and training that EUMETSAT is, of course, also doing in this context. Okay, just to show you how it's evolving, and you just need to look here down on the, I don't know if you can see my pointer, I hope so, on the EUMETSAT Polar System second generation. So the launch is somewhere in 2024. And then we will have a program with 3 satellites each, an A and B. And you saw from yesterday that the 3MI is on EPS-SG. There are other instruments providing also lots of information on clouds, like the microwave instruments like ICI, sublimeter. So there's a lot to gain on cloud properties from this kind of METOP laboratory, I would call that even, on cloud properties. And then we continue this lifetime, at least for 20 years, I would say. So we will end up in the mid-2040s. Some of us will already be retired at that point in time. And then, of course, we expect that there will be a 3rd generation continuing these type of measurements. So why do we need to reprocess satellite data? So there are a couple of reasons. So one is that doesn't play a role for 3MI. That's the addition of unused historic data. So that's a data rescue, and then we do this. But everything else plays a role in this. So normally there's always some gap filling needed. And this comes from the fact that in some cases, the level 0 data are not really converted into level 1. So there are some data gaps, but the level 0 data are still available in archive. So we can fill these gaps. Normally with EUMETSAT operational performance figures, these gaps are normally very small, but still it's worth filling them. Then, of course, we do raw data recalibration. So any improvement in the instrument calibration algorithms is, of course, brought forward into the reprocessing, resulting in a better and improved level 1 product. And that becomes, of course, very interesting at the moment where we have a second 3MI instrument, and you know those 2 instruments are very similar, but they will not be equal. So there needs to be some kind of alignment to get to a consistent time series. And then we will see lots of algorithm improvements. And what I very much liked in Oleg's and Jerome's talk, so there's still a lot to do and to explore. And also the user questions have indicated that. So I think we will see lots of evolution still of these algorithms. Maybe day 2 is not enough. There could be also day 3 and further on. And reprocessing, of course, could really make use of these improvements to further improve the whole data series for bringing this back to the start of the mission. And sometimes there's also some dependence on auxiliary data. So you know that many retrievers are in one way or another supported by things like global reanalysis fields and so. And these are also changing from time to time, which sometimes has impact on the retrievals, not always improving, but mostly improving. So this also needs to be taken into account for reprocessing. So there are a lot of categorical reasons why you really need to do a data reprocessing. So what we do then normally is it's an iterative improvement of data sets and algorithms. So we normally, when we go from level 0 to level 1, or from level 1 to level 2, or sometimes even from level 1 to level 1, so you have a lot of data that we put into our big machinery, have some auxiliary data, take the best suitable algorithm. So sometimes it doesn't, so for many historic missions, we sometimes do not use the operational EUMETSAT algorithm because it has not been further evolved, but outside academia and so has evolved algorithms. So we also use algorithms from others to really produce the best time series of the parameter. And then we produce it, and then there's a lot of effort that goes into the verification and validation and quality analysis, either to comparisons with data, which you also do for retrieval validation. But this is more about looking into time series and also features of time series. So you do rather more time series analysis in this type of comparisons. And also forward modeling is often used to figure out bad phases of the data. When we are satisfied with this process, actually, then only then we archive and distribute data to users. And sometimes we need 2-3 iterations until a series of multiple satellites is actually fit for purpose. So the result of the reprocessing is then in the end comes in 2 things. One is the consistent instrument data at full resolution. So you get basically a real true level 1C, mostly, I guess, for 3MI, the time reference, georeference, and cross-calibrated radiance data sets. And then after applying retrieval to get consistent homogeneous geophysical variables at the same resolution and location. And what we normally do is we make those results available as data records, distinct from the operation of products delivered in real time. So this is a distinct data record with a digital object identifier so that you can really identify and reference the data set in the literature. And of course, these records shall be considered to represent the best quality achievable from a specific instrument with the then available algorithms. So just a few examples so that they are all a little bit from the past, because in the past the observations were not as good as today. So you see much more. So this is an example from an infrared sounding instrument, HERS. And there you can see that there were over time many different types of biases. So I will not go into any detail, but they were in the order, so it's an infrared of 0.5 Kelvin, 0.6 Kelvin, on different calibration versions. And of course, we can fix all those in reprocessing. And then you see here, this was this case for one channel, the operational time series on one satellite. And this is how a reprocessed data series for single instruments look afterwards. So it's much more complete and much more stable. And this is still not cross-calibrated to other instruments on the same, different instruments on the same satellite. Same instrument on different satellites. So this is what you get out of the reprocessing compared to operational products. And that's a great progress. And if you want to study temporal variability and spatial variability, I think this is exactly what you needed. In this case here, this was also a reference, and that we used to actually recalibrate EUMETSAT infrared measurements. And you see here that was the operational data that we used before to do that. And this is a new calibrated time series. You see, you get rid of a lot of scatter in this. And this has tremendous effects then on the recalibrated data. So this is something that will also play a role, I think, in the cross-calibration of instruments on EPS-SG, but probably also on usage with MTG instrumentation. If you look at retrievals, so one simple example is something like atmospheric motion vectors, and you see here two time series from MATLAB, polar atmospheric motion vectors. And you see two curves here, the orange curve, which is the climate data record or reprocessed data record, and the red one, that is what was the operational product at that particular time. And then I have here two dashed lines where new retrieval versions were actually introduced, and only after the third one. So the third one is the one that we use to reprocess. And you see that you have really different data after that in terms of the number of vectors that you could actually derive. So that's already a sign that the data have actually improved through the reprocessing, even on level 1, so that you can really retrieve more winds. But also, if you look into things like wind speed or so, you have now a consistent time series without these kind of jumps in the red curve. And here, in these points, you can also see that there was still gaps in the operational series that were just filled through the reprocessing. So this is typical for, this was even MATLAB, which you can already consider as a very good time series overall, but still it's worth of doing these reprocessing. And this could easily happen, of course, also with 3MI, that you have similar effects in time series of all the many parameters that we derive. So there will be a lot of effort in really checking all of those. So it's a big task in validation. So a little bit on the infrastructure. So just a brief history. So where we come from. So basically, a bit more than 10 years ago here at the headquarters, we started really to consider data reprocessing in a more systematic way. And we had our first environment, which looked very small, and it was really small. And it was still hampered by tons of things like using really ground segment software with all its near real-time adjustments. And I think it was Oleg, I think at least in one of our pre-sessions, he said, okay, we needed to adapt the algorithm to be compatible with a near real-time environment, so make it performant enough. Something to consider for climate, if the quality of the data can be improved even with a slightly slower algorithm, but with better quality of the output. So these things one can also consider if one has the right processing power available to do this. So in the beginning, we didn't have that. So we had a really limited reprocessing periods, and we needed many months actually to do a single record. And we're just targeting a handful of records. And some of you may remember how slow we were. So about 4 years ago, the situation has really changed, because then we get our first real batch processing system, which is much, much bigger. And then we really went to best processors, reprocessing, appropriate change control, and best processors. And we sometimes even run 2 different things for a cloud detection scheme, or so just to compare how it looks on the time series. And everything is online, and a lot of more cores, and some analysis capability included. So this is really, really cool. And now we do full vision and have a pretty high performance. Normally, we do at least 1 year and 1 day is our requirement. And we even fulfill this for sensors like the METOP IRC in terms of processing speed on the current machinery. We work on a new one that we will see, at least in parts, coming next year, which is a kind of a multi-mission reprocessing systems, and that is really optimized for bulk high throughput computing. And we will have the same kind of performance, but it will be able to take more things in parallel than before, because it's just bigger. And we will annually update the capacity, and our planning looks then 5 to 10 years forward with all the upcoming missions, including EPS-SG. That is a kind of medium-sized mission, if you compare that also with all the Copernicus missions that we now also systematically reprocess. And this is fulfilling also a broader scope. So because we do reprocessing to build climate time series, but for METOP or SG, the climate time series is a little bit further out. But I think for product improvements, to have consistent data processing to really see if new retrieval versions are better than before is also an important tool. And I think we will work with our colleagues in RSP very much together to realize that, so that you have also good NRT products based on very comprehensive validation. Okay, so how will we establish that? So we will establish basically this capability already during the commissioning phase of EPS-SG. We have started these kind of things this year with Sentinel 6 as our first pre-runner, where we build this up in the commissioning phase. And then we will do a first consolidation run after the commissioning phase of the instrument using the most actual processor version. So we will first concentrate on the level 1 data, and then level 2. How fast that will be depends on the processors, depends on all the other instruments, depends on what happens during the commissioning phase. So the real timetable for when we do what, that's a little too early to say that. Then we will have following reprocessing events. We will plan that according to the evolutions of the algorithms. And we have seen day 2 products, and also what I said earlier, potential consideration using more accurate algorithm versions. The planning, of course, needs to take into account the joint use of other instruments in this whole framework from level 0 to level 2, and their particular reprocessing needs. So this will also be a part determining what the timetable and the order of reprocessing for EPS-SG, also in relation to MTG, might be. So how I see this today, and don't nail me to this in the next years, because this is what we know today, and this can change. But what one should expect is we will launch that first satellite here, and then we have about 1 year commissioning, maybe a little shorter. But so in 2025, we will probably see the first consolidation run for that. And then depending on the speed, we will have probably after 2 years or 3 years, and then we will go to less frequent, I guess, because the series gets longer, so it takes a little more effort in terms of processing. The progress, it's also probably not that fast. This is the beginning where lots of errors might be fixed. And so then we will have less frequent reprocessing. The normal experience for other data sets shows that in the end, it's something around every 3 years. If it's in a visible UV range, then it's a little bit more often. So because there are other effects on the sensor that you need to deal with. And at some point, so if the frequency of launches is similar to METOP, so we will probably see the second of this A satellites around 2030. And then we will have the same game again. So we will have the consolidation after the commissioning, but we will have implemented this already. And then we will see what events will follow and how we deal then with the SGA2 and the SGA1 together. So there must be elements that tie them together then, so that we still have the time series. Exploitation. I think some of you know that that the EUMETSAT and ECMWF and maybe other European Met services will join in, work on what is the European weather cloud. And this is what we aim with this is, so the motto you can see on the slide here, this shall become the cloud-based collaboration platform for meteorological application development and operations in Europe, and really contributes to digital transformation of the European meteorological infrastructure into a community cloud. So I think in 2025, this thing will have an operational life, or it doesn't exist anymore when it's not successful. But I'm optimistic. So in that sense, it will be available, and I think this is probably the best place to really use reprocessed data, because it just avoids that you need to download all the data, which becomes hefty after a couple of years into the mission, particularly if you want to use this jointly with other instrument data. And it might also be even earlier an option. I think we had this one question about the algorithm round robins. So this could actually be a nice activity for something that could run under EUMETSAT research calls. So there will be research calls for projects that are to the benefit of the EUMETSAT member states. And I think this could be the infrastructure that could be used for round robins very well, and could be designed as a machinery within the European Weather Cloud. I think that is something that one could actually consider to address also algorithm comparisons in an efficient way, and all the collaborators could work on this platform. So summary, so I think the 3MI observations really lead to better understanding of climate system because of this joint consideration of aerosol properties and cloud properties. Reprocessing is just a tool to arrive at best possible temporary consistent data quality over long duration on the METAR-SG time series. And you can probably also connect to others prior, but there is no direct connection, and it's not with EUMETSAT mission. So this is something that would need to be considered in international context. We invest into large-scale reprocessing infrastructures and also into the weather cloud, and we will further do that as far as our money carries, which entirely depends on the member states, how much they want to invest into this. And first reprocessing 3MI, I think we will see this after the commissioning phase in 2025. And then we can exploit the data on the EWC. And this is, of course, a little bit formalistic, because it is for EUMETSAT member states, official duties of the member states institutions of services. So if you're a Met service within Europe, in a country that is a member of EUMETSAT, then you can use it, or in specific projects. And our satellite application facilities are anyway free to use that system. And that's all I have. Thank you very much. I hope it wasn't too long now.
No, Jörg. Not really. It's 4 minutes.
4 minutes. Okay, good. Then I stop share here, and then you can.
Yeah, no, that's okay. Just one question from me. For the reprocessing, you reprocess both level 1 and level 2 data, right?
Yes, we do.
From 3MI, if I say specifically.
Yes. So we do this. We will do this for all instruments of EPS-SG, so not only for 3MI.
Yeah.
The webinar is 3MI, so
yeah.
It's a big task, and but we start to prepare for this. And level 2, I think it's always the case, and we just make that plan. And maybe next year we will know more about this. So on all the geophysical variables derived from the different missions of EPS-SG, it's also applying to MGG and others. So which are the ones that are most important for any climate thing, and or have connections to METOP or even predecessors on NOAA? So those would probably get priority in terms of geophysical parameters. This would only be the aspect of time series, but what I also said is these data, in particular 3MI, will be very useful for process studies as well. And I can imagine that international communities like GBEX, and so they would be very interested to use the data. We have announced that to them that they will come in a couple of years, and I think there is a lot of interest. And that would, of course, also gain points in our priority list to what we do first. But it's too early to say how we do this.
So two things, please post questions to Jörg, and also please participate in the survey before you sign off. Jörg, one more question. Do you closely, I mean, this is also from me, do you closely follow the operational algorithm for reprocessing, or how do you pick, I mean, for level 2, let's say, how do you pick the algorithm? Is it?
Yeah, I think so. In the beginning of the mission, I think it will be preferably the operational algorithms, because they are just brand new. So I mean, we're still working on those, and we have seen there's plans for day 2. So in that sense, it's for the first couple of years into the mission. Normally, EUMETSAT is continuing the development for a while, until, of course, we would start something like the EPS 3rd generation program. So if you really look into long-term planning documents of EUMETSAT, you will see that at some point there will be an EPS-SG. And at that point in time, people like Thierry and Bertrand and so who are slowly moving out of the business of EPS-SG. So it's hard to imagine, because probably 10 years away from now. But we also know that outside of EUMETSAT, there are also many competent groups, and you see all the supporters that was contracted that support the development. So there are others also on other parts on Earth that also do similar things. So it's worth of considering what happens over time to the algorithms. We had in the past specific things, like if you look into Mediasat, just simple things like a cloud mask. There was one operational algorithm for the Mediasat 1st generation and one for the 2nd generation. So if you use either of those, then you would never get to a consistent time series, even of your cloud fraction. So no chance. So you need something that is covering both generations. And in particular, for in the CM stuff, they were working on such a thing. So in that cases, we import algorithms. And that might also be the case in the longer-term future, also for EPS-SG instruments. I mean, we read also papers and we look around, and that's why I'm a big fan of round robins. So it could be a good tool to see, also advance our own developments if others have good ideas. So inclusive is the word that I would use for this type of development, is the best we can do.
Okay. Try to bring up some questions. I think you are just far too ahead, Jörg, with the reprocessing, because people are still warming to the instrument to be launched.
I mean, I cannot reprocess anything. Processing of test data doesn't make a lot of sense.
No, yeah, definitely not. And so I think this is why we still didn't get any questions. But I think for you also, this is just work to be done in future. So I hope this is okay that we don't have any questions. But other than that, I think we are 15 minutes past 4 o'clock here. So I think many of those questions that appeared there, they have been answered by Thierry and Jerome and Bertrand and others. So we will also provide the answers. So I think we can call it a day today. I thank all the presenters from today and yesterday for their excellent presentations. Like I said, we will make this available. I thank all of you, all the participants, but I also thank Stefan Budzinski and also Vesani Teswara today for helping me behind the screens, actually. So thanks, everyone. I hope all of you are here, the panelists. Thank you very much, everyone, the presenters, and bye-bye. See you until the next webinar. Thanks, everyone. Bye.
Bye-bye.
Maybe. Cheers.
Bye.